Hello. All right, this is section 6.6. This will be the last of chapter 6, and then we're going to be combining 6 and 7 together in this next test. So you have to keep going with chapter 7. So chapter 6 is all about factoring, and chapter 7 will be about using that factoring techniques for other things. And here's one. This section it's nice and short. There's only eight problems in here, but it's going to be showing you why we would need factoring. All right. So we're going to be actually taking all these factoring problems and setting them equal to something, preferably 0, and I'll show you how to do that. Okay. I'm also going to show you the graphical connections between these equations, and we're going to be using the calculator a lot to check things and to show you how they're related, so that you kind of have a better understanding of what we're doing here. All right, so all of these problems here are going to be quadratic in nature. So let's talk about what a quadratic is. All right, a quadratic is a equation that's got the highest power as a 2 on the x. Okay? Remember, linear, that had a power of 1 on it. Okay, so then we knew that was a line. It made a graph that looked like that. Well, since this has a 2 on it, then all of these are parabolic. All right? They're either going to look like that or they're going to look like that. We're going to learn all about quadratics in a later chapter. But when we're looking for the x value that sits in here in order for it to make a 0, okay, so the a, the b, and the c are constants, and the x is your variable here. So when we're looking for an x that would make it 0, we're looking for the solution, right, obviously. The solutions, right here. But that's also the x-intercepts, graphically. And these are also called the zeros of the function. Okay? Why is that? Well, let's take a look at a graph. If I have a graph here, and let's say my quadratic just randomly is here, all right? This is asking me, where is the quadratic equal to 0? Well, it's equal to 0 right here and right here, isn't it? Isn't my y-coordinate 0 at both of these points? Sure is. Okay, this is maybe 2, 0, and this will be like 5, 0. All right, so your solutions that make it a 0 are also your x-intercepts graphically. All right? So these are called the zeros of the function, is because of this. All right? So now we have 3 different scenarios that quadratics can come in. It can look like this, where it crosses the x-axis twice, or you know, it could be upside down too. It doesn't really matter. You know, it's going to cross it twice. Or it can just hit once, not cross, but it actually just touches the x-axis, okay? And we have situations like this, and then we have the third, which is when it hangs in the air and it doesn't cross at all. Okay? We're going to be exploring these 2 options today, and then this one is your complex number system. There are solutions to these, they're just imaginary, and we'll look at that in a later chapter, so we're not going to do this quite yet. So we're going to be concentrating on this kind of stuff. So you can see that this right here drives how many solutions you get. Every linear has one answer to it. Well, there's always those exceptions where it says there are infinitely many and there's no solutions, but typically we have the one answer, right? If I gave you, oops, I just dropped my pen there. If I gave you something like this, 3x plus 8, I mean, you're looking for one x value. All right, here we're looking for up to 2 values that can work. Okay, so the highest power drives how many solutions we get. Here we're going to get the 2 solutions, and here we're going to get 1, and here we get 0 real solutions. Okay, so we can get up to 2 solutions. So we're always going to be looking for 2. Sometimes we'll just get the 1. This is a double root. Okay, and I'll show you how those work. I don't know if I have any examples in here, but if I don't in my math lab, I'll make one up so I can show you what I mean by that. All right, and then this one we'll explore later. All right, so we need all that information about quadratics. Okay, so because everything in here is quadratic in nature. Look at, here's a square, 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 square. So these are all quadratics, okay? So we're looking for example, this function, where does it cross the x-axis? Where are my zeros of the function? Or where is y equal to 0? Or what are my solutions? If I put a number in here and here, what number do I need to put in here so that it's equal to 0? That's what I'm looking for, okay? So the other thing that I need in here is something called a zero factor principle. It's called all kinds of things, but this is what my math lab sometimes refers to it as. So the basic principle for a zero factor principle is it says that if two things multiplied, or 3, or 4, or 5, it doesn't really matter, but if two things multiplied equals 0, then either this has to be 0 or this has to be 0. Okay? I can never take two numbers that are not 0, multiply them together, and end up with a 0. Either this one has to be 0 or this one has to be 0, or they both have to be 0 in order for me to get a 0. This is a very powerful, I know it looks really simple, but it's a very powerful solving tool that we're going to look at. Okay? And it only applies to multiplication, not addition, subtraction, or division. All right? We're just talking about multiplication. All right? So let's take a look at what we have up there in problem number 1. We have a squared minus 6a is equal to 0. So I'm looking for an a up to 2. There could be 0, 1, or 2 answers here. That if I plug the number in here, I'm going to get a 0 back out. Well, I don't know how to do that. I can't eyeball it. I have no idea what's going on. So what I'm going to do is I'm going to use this principle here. And I want to make sure that if I have two things equal to 0 that are multiplied, then I can do this. Well, here I have subtraction. I don't have multiplication. But we just learned for, I don't know how many sections, 3 or 4 sections, how to turn addition, subtraction into multiplication. And that's factoring. Okay? So I have to take a look at what type of factoring problem I have here. Well, that's going to be the hardest part of this section, and then all of 7 is determining what type of factoring problem you have. So I usually look at number of terms to start eliminating. Okay, so first of all, let's just list the types of factoring that we have. Okay, we have a GCF, and those can be many terms. It can be 2 or more terms. Okay, there's no limit on the terms, and it's usually just a mess. A lot of times it's just a mess, and there's nothing else that really pops out at you. And if nothing else works, then it's going to be a GCF problem. All right? We also have the trinomials. All right? And those all look like this. It has to be in this pattern. All right? The x squared, x, no x. This one's missing that third term, so it's not going to be a trinomial. And remember, we have 2 different types depending on what a is. When a is equal to 1, we're considered those the easy ones. When a does not equal 1, those were the AC method type. Okay? So we have these. So we're looking for 3 terms in this form. Then there are those trinomials. Then we have the difference of squares. Okay? We have 2 terms for those. They has to be a perfect square minus another perfect square. This doesn't qualify, right? Because 6 is not perfect. Any odd-powered variable is not perfect, so it can't be that. Then we have, I'm going to abbreviate here, factor by grouping. All right, those all have to be 4 terms with nothing in common. Well, again, I've only got 2 terms, so it can't be that, right? Then I've got the difference in the sum of cubes. Oh, we didn't cover those. That was the other class. Never mind, we didn't cover those. Okay. It's just another factoring technique that we would have. I don't think we covered those. I'll have to check. Anyway, those would be with a cube here, which we don't have. We have a square. So it's got to be a GCF problem here because it doesn't qualify for any of these other pieces in here. So I take a look and say, is there anything in common? Well, yeah, I have a common A in there, don't I? Remember, I take out the lowest power variable. I've got a 1 here, so between a 1 and a 6, I can't take anything out. So I'm going to pull out my A. I'm going to divide each piece by the GCF. Remember how to do this? I sure hope you do. So here we have an A left over. These are canceling, and we have A minus 6 is equal to 0. Okay? So do you see how I've turned my subtraction into multiplication? I have A times something. All right? Now I can use this principle. I have something times something is equal to 0. Therefore, either that's got to be 0 or that's got to be 0. One of the two has to, or both, but one of the two has to happen. Well, this one's one answer. A is equal to 0. There's one answer. And here I've turned my quadratic into a very simple linear equation that I can solve. I'll add my 6 across. So A has to be 6. There's my other solution. Remember, I'm looking for up to 2. All right, so let's try these. Let's do a couple things here. Let's first of all, here's my original, A squared minus 6A equals 0. Let's put a 0 in for A. 0 squared minus 6 times 0 is equal to 0. Well, sure, 0 squared is 0. 0 minus, and 6 times 0 is 0, so 0 minus 0 is 0, so that one works. Let's try the 6. So we would have 6 squared minus 6 times, no, 6, that's not an A, Simone, equals 0. All right, 6 squared is 36. 6 times 6 is 36. 36 minus 36 gives 0. So there's my two answers, 0 and 6. So now let's take a look at I want to go back to this kind of stuff. All right, I know that my answers, my solutions, are my x-intercepts. So my graph should look like 1, 2, 3, 4, 5, 6. Should be crossing there and there. And my quadratic, whoa, pretend I hit that. My quadratic should look like that. Because I know where my solutions are, therefore those are my x-intercepts. I just don't know how far down that goes yet. We'll learn that too. So let's check it out. We're going to go into where y equals. We're going to put in our equation right here. Now these are a's. This is just your generic variable, so you're just going to hit that. Yes, it says an x, but the letter doesn't matter. So we have x squared minus 6x. Okay, so that's my equation. I want to take a look at the picture first of all. Yep. It's crossing at 0. It's crossing at 6. Looks very similar. It looks a lot nicer than mine, but it looks similar, right? Now to verify completely that we have exactly 0 and 6, we would look at the table. Oh, I have this set. Hang on. Sorry, I have it set from my other class here. Let me just get rid of all this. Okay, great. Okay, 6 and 0. Y is exactly 0 when x is 6, so that has to be a solution. Then we're going to look at 0. Well, there's the other one, 0, 0. So there's only two spots where y is equal to 0, and that's when x is 0 and x is 6. So therefore, those are my solutions. So you can check them. You know, what I'd like you to do is I'd like you to learn how to do this by hand, factoring. Then I want you to be able to check them by hand, and then I want you to check them with a calculator as well. Now some of these we will not be able to check with a calculator because they'll be fractional in nature, and we can't check, so you have to know how to do both. All right? So here we want to type in an integer or a simplified fraction. Here we have integers, right? And it says to use a comma to separate your answers. So don't put a space between. Just do 0, 6. All right? That's all it wants. No space in between there. It won't like that. All right, let's try another one. Okay, the first thing that we have to understand is that we have an equation set equal to 0, perfect, but it has to be multiplication, which I do not have. I have subtraction. So to turn subtraction into multiplication, I want a factor. So I'm going to analyze, what do I have? What kind of factoring problem? Now I'm going back to this list here. Okay, I'm going to eliminate. First of all, is there anything in common? Is there a GCF in here? No. Could it possibly be a trinomial? No, it's missing that third term. Okay, well then my other choice right here has got to be a difference of squares, right? Because factor by grouping is 4 terms. That's not it. But do I have a difference of squares? Do I have a perfect square minus a perfect square? Yeah, because any even-powered variable is perfect, and 9 is 3 times 3. And I have a subtraction between them. So this is a difference of squares. DOS. All right? So those always break down into 1 plus and 1 minus. Do you see how I'm setting up a binomial times a binomial? All of a sudden I'm turning this subtraction into multiplication. That's the goal. I take the square root of the front one, which would be square root of t squared is t, and the square root of 9 is 3. So I put this in the front and I put that in the back. T's in the front and 3's in the back. Now I've got my subtraction into multiplication and it's set to 0, so now I can proceed. I know that either this has to be 0 or this has to be 0. I've turned my quadratic into 2 separate linear, very easy to solve. So I have t is equal to -3, there's one answer, or adding my 3 across, I get t is equal to 3. So those are my 2 solutions. Okay? So if I squared t, let's say t was -3, -3 squared is 9. 9 minus 9 is 0. If I put a 3 in there, 3 squared is also 9. 9 minus 9 is 0. Okay, so those are my 2 answers. I'm not going to check that one, I know it's right. Difference of squares? Yep, sure. We've got those 2 terms, right? We have the 2 terms. Each piece is perfect. 9 is perfect, and squared is perfect. 16 is perfect. Subtraction between. Bing, bada, boom. I take the square root of each piece. So the square root of 9 is 3, so I'll put that in the front. And the square root of n squared is n, and I also put that in the front. I've got 1 plus and 1 minus. I've got the square root of 16, which is 4. That goes in the back. Okay? So now I've got this times this equal to 0. Perfect. So either 3n plus 4 is 0, or 3n minus 4 is 0. Again, I've turned my quadratic into 2 very easy linear equations, and I solve. So here I would subtract my 4 across. So I've got 3n is equal to -4, and then I divide both sides by 3. So n is equal to -4/3. All right, I'm going to go here. I'm going to add my 4 across. So I've got 3n, this is canceling, is equal to 4. And again, I divide through by 3, and I have n is equal to 4/3. Now here's one that I can't check on the calculator. I'll show you why. All right, my original was this. So I have 9x squared minus 16. Okay. This one goes way down, doesn't even show on there. But you can see that it's crossing at -4/3 is right here, and 4/3 is right there. 4/3 is like 1 1/3, right? But think about what 1 1/3 is as a decimal. 1 1/3 is 1 point, what is it? 1 point, and then a bunch of 3s. A third is 0.3333333 and never ends, right? Okay, so I can't find decimals like this on the calculator in the table. They don't exist. Okay, so I can't ever find my exact zeros on my y coordinates. I know that it's somewhere between 1 and 2 because it jumps from negative to positive, so it's got to cross there somewhere. But I can't find them on here, so that's why you do need to know how to do these by hand. Okay, so the only way that I could check this would be to throw it back in here. All right, should we do that? Yeah, maybe we should just do one. I'll just do one. I'll do the positive. So I have 9n squared minus 16 is equal to 0. So I have 9 times 4/3 squared minus 16 equals 0. Now don't make this hard on yourself. Just let the calculator do the grunt work here. 9 times parenthesis 4 divided by 3 parenthesis squared minus 16, 0. Okay, that's what you're looking for. And then I would do it again for the negative 4/3. But negative 4/3 and a positive 4/3 both squared are the same number, so that's why it works. So sometimes you won't be able to check them with the calculator as far as the exact answers. All right? Well, we can, but I don't know if I want to get into that right now. Probably not. No, you have enough on your plate. All right, let's try one more. We have b squared plus 8b plus 12 is equal to 0. Again, I have to analyze, okay, what kind of factoring problem do I need? Do I have? All right. I don't have anything with 4 or 2 terms, so that's grouping and difference of squares are out. Nothing's in common, so this is one of those trinomials that's set up just perfect. And it's an easy one because my lead coefficient here is a 1. Okay, so remember, those always do 2 binomials. Perfect multiplication. My variable is a b. I have a positive in the back, so that means the signs are the same. They're both going to be positive. Now I'm going to make factors of 12. I'll do that over here. 1 times 12, 2 times 6, and 3 times 4. Since this is positive, I have to add to my middle term, which is an 8, which is this combo, a 2, and a 6. Okay? Now, I can say either b plus 2 is equal to 0 or b plus 6 is equal to 0. One of those two things has to be true. So if I subtract my 2 across, I get b is equal to negative 2. There's one answer. Or if I subtract my 6 across, I get b is equal to negative 6. Here's my other answer. Let's just check one by hand, and then I'll check the others with the calculator. Okay? So I'm going to just randomly pick the negative 2. So I'm going to do negative 2 squared. Wherever I'm going back to my original, and wherever I see a b, I'm putting a negative 2 in, because that's what you're telling me the answer is. You're telling me, huh? I hear you. I wish I could talk to you. I don't like this. I feel like I'm just talking to myself all the time and no one ever answers me. Sometimes that happens in class too, though. I feel like I'm talking to myself. 4 minus 16 plus 12, well, that's got to be 0, right? Because 4 and 12 are 16, 16 minus 16, so that one does work. Okay, and I would check the negative 6. That one would work as well. But this one's probably checkable. So let's get it in there. Let's do x squared plus 8x plus 12. Okay, let's just check to make sure that it's crossing. Yeah, it looks good. Negative 2 and negative 6. And then we would double check for sure. We're in the negatives here, so there's one of them, negative 2 and 0. It's exactly 0. We need it exactly to be 0, and negative 6 and 0. Perfect. So you would just plug those in. Negative 2, comma, negative 6. Okay? All right, so that's the same. Okay, that's a trinomial. It's an easy trinomial. What about that one? That one is not a difference of squares because this piece of it right here is messing it up. Remember, on difference of squares we have to have even powered variables. This is an odd-powered variable. So I would look at that and go, okay, it's almost a difference of squares, but it's not. So, well, let's do that one. That one's just slightly different. Maybe, I don't know. Not really. All right, talking to myself. All right, so I would look at that and say, well, if it's not a difference of squares, and it can't be anything else like the trinomials in the grouping because it doesn't have enough terms, it's got to be a GCF and it's a t. So it has a t in common, right? Take out the lowest powered variable. Divide through by t. This becomes t minus 9. All right, so here's one answer, t equals 0. I know I did that in the beginning. Sometimes this messes people up. Or t minus 9 is 0. So adding my 9 across gives me 9. So there's my two solutions right there. All right. All right, so this one, this would be a good review for my AC method. First of all, I don't have this thing set to 0 like I always have. I've always had it set to 0. This is set to 16. There's no rule about two things multiplied equals 16. All right, it's always equal to 0. So what I'm going to do first is I'm going to subtract my 16 across and force it to be 0. Plus 2x minus 16 is equal to 0. Now I've got this trinomial, not an easy one, right? So I'm going to go back. I suppose this is really good practice for us. What is 3 times 16? 48. Okay, so remember a times c is 48. So I'm going to make factors of 48. Now I have a negative back here, so that means they have to subtract to a 2. Right? And I can, if you can think of it, write it down first. Isn't 6 times 8 48? And isn't 8 minus 6 2? Yep. All right, so what we're going to do is we're going to split our middle term of a 2 using this combo. So I would rewrite that as 3x, and I've got a positive 2, so I want the positive 8x minus 6x minus 16 is equal to 0. Okay? This gives me a positive 2. Okay, what's common here? We're going to group, remember? And group. Well, there's not much that's in common, just the x, right? So I'm going to divide through by x. This gives me 3x. My x's here are canceling, plus 8. What's in common here? Well, not a whole lot again, but a 2 is in there. And since both of these are negative and these are both positive, I'm going to want to pull out the negative 2 to make them positive. So here we have a negative 6 divided by a negative 2 gives me a positive 3 with the x. See how I'm matching these? And a negative 16 divided by negative 2 is a positive 8. So I've turned my 3 terms to 4 terms to 2 terms. These 2 terms have the 3x plus 8 in common. And what's left are the outside pieces, x minus 2. All right, now I have multiplication equal to 0. So now I set each piece equal to 0 and solve. And I'm really running out of room here. So I can say either 3x plus 8 is equal to 0 or x minus 2 is equal to 0. Well, this one's really easy. Here's one solution. All right, here we're going to subtract the 8 across. So we have 3x equals negative 8. Dividing through by 3 gives me x is equal to negative 8 thirds. All right, so how do we check that? Well, we could check it by hand, right? Let's just try the 2 because it's easier. I'll go over here. Got to get rid of all this. Okay, so wherever I see an x, I put a 2 in there, in the original, plus 2 times 2, and this is supposed to equal 16. Well, let's see if it does. Again, let your calculator do the grunt work. 3 times 2 squared plus 2 times 2. 16. It works. Now if I put this -8/3 in there, that would also work. Okay, now I can't check that on a calculator graphically because 8/3, look at what 8/3 is. 8 divided by 3. It's this never-ending list that I can't find on there. I can find decimals that end. If it was like 2.6, I could find that, but I can't find 2.66666 forever. So therefore, you do need to know how to do these by hand. Okay? And the last one that we have is a mess. Let me get a nice fresh screen for you. Only for you. All right, what do we do with this? This disaster. No, I'm just kidding. Well, we'd have to, first of all, get it set equal to 0. That's our goal. Well, what I'm going to try to do is I'm going to try to clean this up a bit. I don't want these parentheses in there, so I'm going to distribute first. So x times 5x is 5x squared. And x times a -8 is -8x. And that's equal to 13. And now I can subtract my 13 across. And voila, it's a trinomial using the AC method, right? Which I'm not going to do because I just did one, but you can finish this one. It's exactly like the one that we did before. Okay, so all you have to do is you have to, rearrange it so it looks more normal. You want it to look like a normal trinomial. Normal trinomials don't have parentheses, and it has to be set to 0 in order for that a times b equals 0 principle to work. Okay? And that's it. That is chapter 6 in a nutshell. Factoring is one of the most important things in algebra. As much as people hate it, it just keeps coming back to haunt you. So you got to know it really well. We're going to use it in college algebra. We're going to use it in chapter 7. We're going to use it in math just continually. So practice up, and I will see you for chapter 7.